In this video, you're going to see the details of how the Adaboost Ensemble learning is carried out. So, as a first step, what we do is we initialize the weights of each training sample. As we said before, that in Adaboost algorithm, the samples are weighted. So, what we do as a first step is initialize the weights of training samples. And as we said before, that initially there might be no any justifiable reason to have different samples having different weight. So how we initialize is just we can give equal weight to each sample. And so what we do is let's denote the weight of a sample I as alpha sub I at the first time step. So it's basically 1 over m, where what we say is m is the total number of training samples. Okay, so initially we give equal weight for every training sample. That's for our step 1. Now what we do is in the step number 2, we train a weak learner. We train a classifier, which we call in this literature as a weak learner. Okay, using the weighted training samples. Okay, and what we do is because the samples are weighted, so even the error rate we compute is the weighted error rate. And the classifier, which is again for most of the literature, it can be any classifier, but mostly in the literature, people use the example of decision stumps because it's easy to explain how it works. So what we do is the classifier has to do the best it can, and based on the weighted training sample. So what we say is also that we compute the weighted error rate. Okay. So let's call this weighted error rate as epsilon at time step t. Okay. For t being 1, 2, up to let's say k, we decided for example that we will go up to k weak learners. So k individual classifiers in our Adaboost ensemble. Now to just give you an idea about what do we mean by weighted samples. So what is the weighted error rate? To understand that, let's take an example here. So the example is, let's assume that we have sample S1, the training sample S2, S3, S4, and S5, 5 training sample. And let's assume the current weight of that sample is 0.4, another one is 0.7, another one is 1.5, the fourth one is 1.1, and the fifth one is 0.3 for some reason. And let's assume that these 3 samples were misclassified and these 2 were correctly classified. So what is the weighted accuracy or weighted error rate of those samples? So what is the weighted accuracy if this the current learner, the classifier, performs this and it misclassifies these 3 points and correctly classifies points? What is the current error rate for that classifier? So the weighted error rate, what we'll say is the weighted error rate at that time is nothing but the error rate 0.4 plus 0.7 and plus 0.3 over all of the sample weights. So 0.4 plus 0.7 plus 1.5 plus 1.1 plus 0.3. And if you see this, it's going to be close to 7 plus, yeah, so it's basically 1 point, is going to be 1.4 over, you have 2.6, so it's 4.0, right? And if you do the calculations, you get 0.35. So this is the error rate of the classifier, although it misclassifies 3 of the 5 points. Why is this error rate is lower than, assuming that these all samples were same weight. So again, assuming if all samples had same weight, so what would be the error in that case? The error in that case would be 3 out of 5, right? Which is 0.60. But because the samples are weighted, the current error rate of that classifier is 0.35. It's not 0.60. Again, because of the idea of weighted samples. So this is very important concept here, which has to be very clear, right? So our classifier tries to do the best. It tries to minimize the error rate based on the weighted samples. So the error rate is also the weighted error rate. Good. Now, once we have these, the classifier being trained, what we have to do is also, based on the weighted error rate a classifier has, we need to assign a weight to the classifier. Because if you remember what we said in the ensemble learning is that the overall classification is the weighted classification of individual classifier. So what about the weight of a given classifier? So to understand that, what we do is here, based on the performance of a classifier on the weighted training samples, we assign the weight. So the weight of the classifier, is given by this formula. So let's say the weight of a classifier at time step t equals to half the natural log of 1 minus the error rate of that classifier over the total error rate. This is the equation how we can get the weighted error rate for a classifier. Now, a question can be, how do we get there? So from where does this equation come up? Now, in a separate video, we are going to explain this equation, but it's enough if you know at this stage that this is the equation, right? So basically what happens is the Adaboost uses exponential loss, and you aggregate all the exponential loss, try to differentiate and see the minima, which is basically you get this equation. So in a separate video, we are going to look into it. How do we get this equation? But for the time being, let's take some examples to understand, right? So let's take some examples here. Okay. So as a first example, let's take the same thing, that a classifier has a weighted error rate of 0.35. So what's the weight of that classifier? The weight of that classifier would be half the natural log of 1 minus 0.35 over 0.35. And again, if you do the maths, what you get is close to 0.3095. So this is the weight of a classifier whose weighted error rate was 0.35. Let's try to understand more intuition behind it. So let's assume if the error rate of a classifier was 0.1, in a sense that the weighted accuracy of that classifier was 0.9. So what's going to be the error rate of that particular classifier? So the error rate is going to be half 1 minus 0.1 over 0.1, which is nothing but half log 9, which is nothing but again 1.098. So you can see that if the error rate goes down, the weight of the classifier increases. Now what happens, assuming that the best a classifier can do is to achieve an error rate of 0.5? What happens in this case? So if you plug in this error rate in this equation for the weight of the classifier, you see half log 1.0.5 over 0.5, and half log 1 is basically 0, right? So what we are saying is if your classifier can do the best to achieve a the weighted error rate of 0.5, it's a random guess, a random classifier. So there's no weight for the classifier. Okay. Another interesting thing is, what if the error rate of the classifier is 0.9? The weighted error rate is 0.9. What would be the weight in this case? So if you plug in here, you'll see half natural log 1 minus 0.9 over 0.9. Okay, which is exactly, if you do the calculations, you get minus 1.098. And this is something interesting if you see. So if the error rate was 0.1, we get 1.098 as the weight of the classifier. Whereas if the error rate is very high, we still get a high weight, of course, a negative high weight. That's interesting to understand the intuition behind it, because what we say is if you are doing binary classification and the error rate is 0.9, which is below 0.5, we can always reverse the prediction of that classifier. So actually getting a very bad error rate, if you just reverse the prediction, you get very high accuracy, right? So error rate of 0.9, and if you reverse all the outcome, you can get an error rate of actually 0.1. So, and that's why we see that the classifier is still having a high weight, but the negative, because whatever it says, we take the reverse of it. So if it says class point is a positive class, we take it as a negative class with this weight. If it says a negative class, we say it's a positive class with this weight, and so forth. So this is something interesting to keep in mind. Okay. So basically what we want is we want a weak learner to have our weighted error rate of higher than 0.5 or lower than 0.5. Both of them is okay, but not 0.5. So this is the idea here. Okay. So these are the first two steps. Now let's continue here. So what's this third step? So now we had the weight of the classifier based on the training and the weighted error rate. Okay. Let's understand now the what we do as a step 3. So what we do in the step 3 is we reweigh the training samples. So we say reweigh the training samples based on how the classifier in the current stage, in the current time step perform, right? So reweigh the training samples for the next cycle. Okay. Now, how do we reweigh the training samples? So we say the equation here is that alpha sub I, the weight of a training sample I at time step t plus 1 for the next time step is nothing but its weight at the original time step, the previous time step, I mean, times e to power of minus the weight of the classifier at time step, the output of the classifier at the time step, times the actual label of that sample, x of I. Okay. Now this is interesting to keep in mind. What does this mean? So the ht of x of I and y of x of I. So y is the actual label and ht is the output of the classifier at the time step t. So what happens is if the classification of the sample was correct, so ht, so it could be, let's say it's a positive class, so the y is +1 and ht is also +1. So +1 into +1 remains +1. And if it is even if it is a negative class, so let's say st is -1 and y is -1, so -1 into -1 is again +1, right? So basically what this translates into is two different scenarios, right? So let's try to understand the true scenarios. So the two scenarios are this: that the weight of the sample I at time step t plus 1 is the previous time step weight of that sample, okay? into e to the power of wt if the sample was correctly classified. And its weight was the previous weight times e to the power of wt if incorrectly classified. If a sample is incorrectly classified, you can easily see that if a sample was incorrectly classified, so the output of the classifier times the actual label is always going to be negative, and negative times minus wt becomes plus wt. So basically, what do we understand from this? We understand that the weight of the sample will be reduced for the next time step. If it was correctly classified this time step. And the weight of the sample, the training sample, would be increased if it was incorrectly classified at the current time step. So we give more weight for samples which were incorrectly classified now, so that later it's classified correctly by other weak learner. So this is a very important concept here again. So we have to keep this in mind, right? So this is how we have the weight of the classifier. Now, if you try to understand much more into details, you can understand that this can also be understood as alpha sub I of t times what is e to the power minus wt. If you remember the wt, right? So wt is nothing but this equation, right? So if you do e to the power of half log the natural log 1 minus the error rate over the error rate, what happens is what we get is we get, I'm sorry, e to the power of minus half log 1 minus et, the error rate, if it was correctly classified, and e to the power of half the natural log 1 minus the error rate over the error rate if it was incorrectly classified. And if you can easily see, this can be simplified to, and if it is negative log, so you can see that the denominator and the numerator gets reversed, and half is, you can square it, so e and ln cancels. So basically what you get is you get this equation, right? This if the sample was correctly classified, right? Similarly, you can see it is this equation if it is incorrectly classified. Okay, so again the same idea here. So these are very important understanding to keep in mind how the weight of the samples are updated. Okay, now instead of taking the example of how to reweight, we take it a bit later because there are some interesting insights to about the reweighing of the samples. Okay, so let's move forward now. So we reweigh the training samples, but what can happen is we have to keep something in mind. What can happen is this, that because a given sample might be correctly classified successively, so the first classifier classifies it correctly, the second, the third, and let's assume k is 100 or 200 or something, and let's say the first 10, 20, 30 times the sample is correctly classified. So this the weight of that sample will become smaller and smaller and smaller. It becomes very small. Similarly, if a sample is a hard one, it gets misclassified initially many times, and its weight keeps increasing again and again and again. It becomes too large, right? To deal with that, we have this idea of reweighing rescaling the sample. So the weights are as we see now. What we do is basically then we reweigh the sample. So what we do is, I'm sorry, we normalize the sample, right? So we normalize the reweighted samples. So how do we do that? normalize the weighted samples, right? Okay, so what we need to do is basically, again, the same idea. A sample I at time step t plus 1, its weight is going to be either of the two cases, right? So it's going to be the previous weight at time step t times this if it was correctly classified. But now we divide this to normalize it by a factor called z, and we see what is that z. Similarly, if it was incorrectly classified, we have this, the original non-normalized weight, we basically normalize it by z, right? So these are the two cases of how we normalize. Now the thing is, what is z basically? The z is there just the sum of the new weights. So we say z is a summation of I equals to 1 to m. You have m training samples. The samples weight. That's it. So this is z. Okay. So this is how we reweigh the sample and normalize the reweighted samples. Okay. As I said before, we'll take an example shortly, but this is the idea here. So once we have done these steps, what we do for the whole algorithm, we say repeat. Okay. Steps 2 and 3. Okay, which is reweighing the sample, training the classifier on the reweighted sample, assigning weight to the classifier, and then reweighing the sample, the training sample, and normalizing the reweighted sample. We keep doing that, right? How many times we do? We do until there are many stopping criteria, right? So we until what can we do? So for example, sometimes we fix the k until t equals to k. The how many time steps we want to go. So k, so means we will have k individual weak classifier. Or for example, you reach a desired accuracy. Desired accuracy is reached. Of course, the best could be that you have no error rate, right? So you might also stop there. But it could be that you say, okay, keep learning individual weak classifiers and keep growing the ensemble as long as the error rate on the training set is greater than 10%. So you keep doing that, right? So these are some possible scenarios where you stop, right? And also there can be a situation that at a given time step t, the best error rate, the weighted error rate is 0.5. And you know, we are not going to consider 0.5 because it's a random guess scenario. So we know that nothing best can be done. So we stop here. So these are some possible stopping criteria. Okay, you specify the k, the number of weak learners you want in the whole ensemble, or you specify that what should be the maximum accuracy you want, or you say that if actually there's nothing more improvement you can get. So you stop. Okay, so final, what's the final ensemble? The final ensemble, what you get, let's assume, let's denote that by capital H of X. Okay. So capital of H of X is nothing but the weight of the first classifier, the output of the first classifier, times the weight of the second classifier, the output of the second classifier. You keep doing till the kth classifier, the output of the kth classifier. So you do the sum of that and you check the sign, right? So basically we can state it like this. Okay, p equals to 1 to k wt ht of x, and this is the final output of our ensemble. Just to take an example to make sure that we understand the idea here. Okay, so let's add an example, right? How it works. So let's say that I have the first weak learner. So assuming that we have total of 4 weak learners, H1, H2, H3, and H4. And the weight, the weight of the first one is 2. And the weight of the second one is 1.5. The weight of the third one is, let's say, again 1.5. And the weight of the fourth one is 0.5. Assuming these are my weights for individual weak learners. And say for a given training sample, this predicts a positive class, this predicts a negative class, this predicts a negative class, this predicts a positive class. Okay. So what would be the what would be my final output of the Adaboost ensemble? Okay, because these are weighted, so we say our final output is nothing but the capital H for the sample X is nothing but what? We have a positive class and its weight is 2 plus a negative class times its weight plus another negative class times the weight of that classifier plus the positive class times the weight of that classifier. And if you do this math, basically you get plus 2 and 2.5. So basically you get 2.5 minus 3.0, which is nothing but minus 0.5. And because it's a negative value, you say the final output is the negative class. So this is the final output of your ensemble. So this is how it's going to work. So I hope this is clear right now. So let's stop here and then we continue on understanding the insight of mathematical insights on how the reweighing and normalizing can be simplified. Okay, so let's stop here. Okay, so now let's try to understand how this is going to work, right? There are some interesting mathematical insights which was not presented by the original authors of the Adaboost classifier, Jan Freund and Classifier, but it was later discovered, which is something very interesting. So let's understand this. So we say that Z, the normalizing factor for the weighted training sample is nothing but the sum of the weights of all the training samples, right? So we say this was Z. And if you see that this is nothing but summation of two different things. Those samples which was correctly classified, you want to sum those weighted samples, okay, plus those samples which was incorrectly classified. You want to find the sum of those. Good. So basically what we are saying here, correct means for those samples, the H, right, was equal to the actual label, right? And incorrect what means is that at time step P, the weak learner, right, has a different label than the actual label for that particular sample. Good. So to understand this, okay, we say we can write, as you saw before, that this thing, if it's correctly classified, is nothing but alpha sub I of time step T times epsilon T 1 minus epsilon T. We can see this. This was there, right? So this is the same thing I'm using here again, this bottom one, right? So this is if it was correct, plus the summation of incorrect which is nothing but alpha sub I of t times 1 minus the error rate over the error rate. These are the two different scenarios. So those samples which were correctly classified at time step t and those which were incorrectly classified. Okay, good. Now let's try to understand this more. Now, if you look at this, what is the summation of, let's take for the timing, let's start with this one. What is this term? What is this term here? What is the weighted sum of all the samples which was incorrectly classified? That's nothing but the error rate, right? So this is nothing but the error rate. Okay, so we say error rate times 1 minus the error rate over the error rate. Similarly, if you see, if it was correctly classified, so the weighted samples of the correctly classified is basically nothing but the opposite of the error rate, which is the accuracy. So 1 minus the error rate times the error rate 1 minus error rate. Okay, these are the two things. So if you do some math here, okay, what do you get? You get this term to be nothing but error rate 1 minus error rate. And again, if you see here the same thing, error rate, if you get inside, this cancels, you get basically the same thing, error rate 1 minus error rate at time step, which is nothing but, we can say z is nothing but 2 times the square root of error rate 1 minus error rate. So this is important to keep in mind. This is one important insight. Okay, this is our z. Good. Now let's try to understand that what happens now. So what happens is, let's see. We said that the weight of a sample I, okay, at time step, okay, I'm sorry. So weight of sample at time p plus 1 is nothing but, you have two scenarios, right? I'm sorry. You have alpha sub I of t, okay, times, what do we have? If it is correctly classified, the error rate 1 minus error rate over z, and alpha sub I of t times 1 minus error rate over the error rate times z. This if the sample was correctly classified, if the sample was incorrectly classified. And again, this is exactly what we did here, right? The same thing, this particular part, nothing new. Okay. So, but now what we can do is we can substitute the value of z we found last time. So, which we can rewrite as alpha sub I of t times the error rate 1 minus error rate over 2 times square root of error rate 1 minus error rate, and alpha sub of I times 1 minus error rate over error rate whole over 2 times square root of error rate 1 minus error rate, right? We just substituted the value of z. Okay. Now this is interesting because if you see this, what do you get? You can simplify this part, right? So how can we simplify this? So let's look at this. So if we have this square term here, you put it down. So what do you get basically? So yes. So what we are saying is this is nothing but alpha sub I of t times, okay, so let's put 2 here. What do we get here? We get error rate, right? Okay, and here we get again error rate 1 minus error rate square, isn't it? And this can get cancelled. Basically, you're left with alpha sub I of t, okay, times 1 minus error rate, this thing. Similarly, if you solve this one, what do you get? You get, this is nothing but alpha sub I of t, okay, over 2, this 2 here is here, times the square root of 1 minus error rate, okay, over error rate, both of them is there, square 1 minus error rate. And these two cancels, which is nothing but alpha sub I of t over 2 times 1 over error rate. Now, what does this tell us? This tells us something interesting. So what is the sum of all the weighted correct samples? So what is the sum of weighted correct samples? Sum of weighted correct samples is nothing but summation of correct alpha sub I t plus 1, right? And if you use this equation here, which is nothing but summation of all the correct ones, right? Alpha sub I of t over 2 times 1 over 1 minus error rate. And now if you see, what is the summation of all the correct weighted correct samples, right? Which is nothing but 1 minus error rate. So what do you get? You get 1 minus error rate over 2 times 1 over 1 minus error rate, which is nothing but half. So what we understand? We understand that the normalized weighted samples, or if you you look at all the correct samples, basically it normalizes, and the sum of all of that is again half, which is also true for the negative ones. So what is the sum of weighted incorrect samples? So we say what's the sum of incorrect alpha sub I at time step t plus 1. This is nothing but, right, alpha sub I time t over 2 times 1 over the error rate. And this is the sum of all the incorrect ones, right? So what does this give us? What is the sum of all the weighted incorrect sample? Is nothing but the error rate. So we say error rate over 2 times 1 over the error rate. Again, we cancel it, we get half. So this is a very important insight, a very interesting insight actually. It tells us that what you do, you don't have to do the logarithmic and exponential to get the weights of the samples at any given time step. What you need to do is basically renormalize the incorrect samples to half and renormalize the correct samples to half, and that's it. You get the final weights of the sample for that particular time step. That will solve the purpose. Now to make this clear, let's take one quick example. Okay. So an example to understand that. Good. Let's assume we have S1, S2, S3, S4, S5, 5 samples. Okay. And assume, again, as a start, there's no reason to have different weights, assuming all of them has the same weight, which is nothing but 1 over 5. Each sample has a weight of 1 over 5. And also let's assume that the first classifier classifies this sample correctly, this one correctly, Let's assume it misclassifies this, it classifies this correctly, and again misclassifies it. So what we need to do, we need to reweigh the samples, right? So how do we reweigh the samples? One way is to again, even for understanding it, what's going to be the error rate, right? So let's try to first understand what's the error rate of the classifier at the first time step. Okay. I'm sorry. What the error at the first time step is nothing but, because all the weights are same, is basically 2 over 5, which is 0.4. Now what you can do to reweigh the samples are, we understand that those samples which were correctly classified, its weights will go down, and those which were incorrectly classified, its weights will go up. And again, we can use this formula to understand, or we plug in that we say alpha of a sample at time step t plus 1 is nothing but the previous weight, right, times e to the power of minus wt, or e to the power of positive wt, it depending on it was incorrectly classified or correctly classified, and then finally we find z and renormalize them. Instead of doing that, we understand from our previous discussion that what happens at the end is all the correctly classified samples, their weight gets normalized to half. So basically what we need to know, we need to do is we have to look at this sample, and this sample. Now we have to reweigh them so that the sum of them becomes, I'm sorry, we have to renormalize them so that their sum becomes half. So what we can see is basically is nothing but 1 over 5 over summation of all of that. So 1 over 5 plus 1 over 5 plus 1 over 5, the three correct samples, times it's renormalized to half, which is nothing but, what do you get? You get, if you do the math, you get nothing but 1 over 6. So this becomes the weight, new weight of this sample. Similarly, this sample will have a weight of 1 over 6. This sample has weight of 1 over 6. What about these two? Because there are only two samples and had initially same weights, we have to renormalize it to half, and initially they have same weight, so nothing, it's simple that its new weight will be a quarter. Because we have two of them, you add them, the weights add up to half. So these are the new weights, okay? So now, again, just to understand that, okay, let's assume this was correctly classified, this was correctly classified, this was wrongly classified in the second time step, in the time step 2 by the second week learner, and this was correctly classified. Good. Now, based on that, what do we get? We need to reweigh and normalize it. And we said instead of doing that in the longer way, what we can do is we can look at all the correctly classified samples and renormalize so that their new renormalized weight, the addition, it sums up to half, basically. So what we can do is, again, the same idea here. So let's do, what's the new weight of this? So the new weight of this is nothing but, I'm sorry, is nothing but a sixth over the summation of all of that. Okay, the summation of the correct samples. So it's 1 over 6 plus 1 over 6 plus 1 over 4, and it has to be normalized to half. And again, if you do the math, you have 6, so you have 1 plus, so the, okay, let's say the common is 12, so you get 2 plus 2 plus 3, right? So you have 2 plus 2 plus 3, 5, 7, right? So you get basically nothing but 1 over 6 over 7 over 12, and the whole thing is multiplied by a half. Is it? And if you again do some maths, you find that basically this becomes nothing but 1 over 7. And because this is also the same initial weight was there, so this will again be renormalized to 1 over 7. And this one will be actually a bit different. So it will be nothing but 1 over 4 over 7 over 12 times half. And this is nothing but, actually, this weight will be nothing but 3 over 14. Now, regarding the two misclassified ones, you have to rescale their weights to half. So what does the weight become? So it becomes, the first one becomes 1 over 4, and 1 over 6 plus 1 over 4 which is nothing but 5 over 12 times half, and this is nothing but 1 over 6, 5 over 12 times half. And again, if you do some maths, you find that this is nothing but 3. Let me see here. So 1 over 4. Okay, I guess it's going to get to 3 over 10. And this is going to get to 1 over 5. And just to verify that your answers are correct or no, let's see what's the sum of the reweighted samples for the samples which are correctly classified. So what is 3 over 14 plus 1 over 7 plus 1 over 7 is nothing but 2 plus 2 plus 3. So it's 7 over 14. It's nothing but half. What about 3 over 10 and these two? Because these were the two which was incorrectly classified. If you see, let's say it's nothing but 3 plus 2 over 5. So 3 plus 2 over 10, which is nothing but 5 over 10, which is half again. So we understand these are the new weights. And that's how we can always re-normalize the weights of the correctly classified samples and the incorrect classified samples. So this explains us the main idea of the Adaboost algorithm. In the next video, I'll explain why we have the weight of a classifier being half times the log of 1 minus error rate over the error rate. And another video I'll post which explains one working example of an Adaboost ensemble learning. Okay, thank you very much.